I'm just going to go through some figures from model simulations that are presented in the same GFDL report that we looked at the summary from. I'm not even going to say much, but you can see that how difficult this business is of not only projecting into the future about what cyclones will do with global warming, but even trying to interpret the past, as we know already that there are data issues, there is reanalysis of hurricanes which have reprocessed the hurricane data, but again to find the data for maximum sustained wind speeds and so on is not so easy. Nonetheless, we can run through the figures to see what the models are saying. So this is from a paper from Bin Wang's group, which we will use to just summarize the power dissipation index. So a storm activity index, SAI, such as the annual ACE, accumulated cyclone energy and accumulated power dissipation index, can be written in a general form. SAI is sum over 0 to n, sum over 0 to tau, Vmax n, where Vmax is the maximum sustained wind speed of tropical cyclones. N is an integer. We will see what that is. That stands for. The two sums denote summations over the lifetime of each tropical cyclone at 6-hour increments, and for all of the tropical cyclones N that occurred each year in a specific basin. So you can do this by basin in each hemisphere. When n equals 2 and 3, this n, small n, is 2 or 3, SAI becomes the annual ACE and accumulated power dissipation index respectively. So they have basically created a common index based on all these various different formulations. When n equals 0 and 1, SAI can be called the annual accumulated tropical cyclone frequency, TCF, and tropical cyclone momentum. According to one, except for TCF, SAI is a function of the intensity, lifetime, and annual frequency of tropical cyclones. TCF is independent of tropical cyclone intensity or maximum sustained wind speed, Vmax. Okay, so remember that intensity is averaged typically over 1 minute or 10 minutes, depending on whether it's in the North Atlantic or in the typhoon region and the Indian Ocean and so on. I'm not going to try to interpret these figures too much, but you can read the papers and the reports for details. I do want to show them. So here we are looking at percentage change in power dissipation index, PDI, based on absolute SST for 1946 to 2007. There is the historic period, and then there is the projection. And here are the high resolution model projections that you can read up the captions of. So we are looking at annual observed power dissipation index. Is it showing any trend? You figure it out. 5-year observed PDI, so you run a 5-year running mean, and you have a trend here which coincides with the acceleration of the warming since the 1980s. Statistical 5-year PDI downscaling of global climate models over this period. Individual models, 24 models are used, and the average of 24 models is shown here. So the 5-year observed PDI and 5-year PDI based on observed absolute SSTs is shown. What do we mean? Basically, we cannot say for sure whether the tropical cyclones care about the absolute SSTs or the deviation from the climatology, so anomalies. For example, whenever we do climate modes like El Nino, Indian Ocean Dipole, NAO, PDO, Atlantic Nino, AMO, whatever you take, we are always looking at anomalies, and a lot of the teleconnections, processes, predictions, everything is done with respect to anomalies. But here you see that the answers or the historical behaviors and future projections and all should resolve this issue of whether absolute SSTs matter, or we can do it based on relative SST, in which case you get a very different answer. That's what I'm going to point out and let you catch up on what the details are. So percentage change in power dissipation here based on relative SST. Again, annual observed PDI, 5-year observed PDI, 5-year PDI based on observed relative SST. The correlations are shown here as well. So you can see that 5-year PDI based on observed relative SST here versus the same thing here are remarkably different. Okay, so you can see there is a strong trend here in the statistical 5-year PDI downscaling into the future, whereas here it's very different. Okay, so here again statistical 5-year PDI downscaling of global climate models, individual models, and average of 24 models. So this is a basic fundamental science question that has to be resolved for planning for the future. There are other details. For example, the near-term projections of this sort tend to depend on model uncertainties, like if the model is not able to produce an AMO, Atlantic Multi-Decadal Oscillation, can it do a good rendition of future cyclone trends? Or considering these are coupled models which are used for projection, which have low resolution and don't explicitly resolve cyclones as such. So how do we interpret these future projections? All those sorts of questions I'm going to leave up to you to catch up on. The data, as you go back, especially for weaker ones, tend to have biases. There were no satellites, there were no recons. Landfall cyclones had obviously a bias because they were better observed, let's say, and so on. But there is a hurricane reanalysis data set that's produced, which is adjusted for estimated missing storms. So there is some data reprocessing of the past. We are looking at hurricanes, tropical and subtropical storms. So adjusted annual storm count, you can see here. There are lines drawn here for trends. This is linear trends we will look at in a minute. Adjusted 5-year storm count, adjusted. VKO8 additive adjustment, VK08 multiplicative adjustment, and 95 method uncertainty. So I'm not even going to say what those are, but you can go and read about the reprocessing. So you can see the stark difference between the additive adjustment and multiplicative adjustments that give us these numbers. So if you look at storms per century trends over 1978 to 2006, that's 1.6 storms per century. If you take a shorter period of 1900 to 2006, you get a remarkably different number. You get 4.39 storms per century. So how this little period can make, can make a difference in the trend. That's not a small difference, right? So these things have to be kept in mind when we are looking at cyclone trends and responses to global warming. This is another figure from the same report. Atlantic Basin hurricane counts from 1851 to 2006 with a 5-year running mean. We are looking at major hurricanes, 1980s onwards. Is there a strong trend? US land falling hurricanes, not such a strong trend here. And all hurricanes, and is there a trend here? So this is kind of consistent with the exceedance figure we saw before about the fraction of hurricanes that reach categories 3, 4, and 5. So there may be something, but again the question is whether attribution can be done, where the exceedances, are they really related to anthropogenic forcing, or are they part of the natural variability? If so, how are they related to these sorts of normalized tropical indices? We are looking at global mean temperatures. We know how the warming trends have been. Here is the standard deviations. Tropical Atlantic SST, raw hurricane counts. Okay, there is a trend. Are they related? Trends always correlate, so we have to remember that. Plus, you have to remember whether that this will differ based on whether you look at total SST or relative SSTs, right? Adjusted hurricane counts. Now you don't see the trend anymore. US landfalling hurricanes, not such a trend. Atlantic SSTs relative to tropical SST. So you can see the difference here is quite stark, right? So we are left with a lot of questions, but Atlantic hurricanes for 1980 to 2012 simulated versus observed. The correlation between models and observed is quite high, but the linear trends are not the same. So model here is in red and observed are in these black dotted lines, the circled lines. So the linear trends are 0.18 storms per year in the model, which is slightly higher than 0.13 storms per year in the observed. Again, we don't know. This doesn't mean that it immediately can be related to anthropogenic forcing, and we still have to worry about models' inabilities to produce even El Niño's Atlantic multi-decadal modes and El Niño's impact on the tropical Atlantic and tropical Atlantic cyclogenesis versus the North Atlantic AMO and so on and so forth. Other figure here, looking at number of occurrences of observed in terms of maximum wind speeds, observed control and warming run. So you would hope that the control run will produce observed behavior, and then you can look at how warming would shift that distribution. And you can see that observed have maximum occurrences in the this maximum wind speed range, but have a longer tail, whereas the control run and the warming run produce quite a different distribution of maximum wind speeds in terms of number of occurrences. They don't have a very long tail at all here, but they have a huge peak here in the range of, let's say, 30 to 50 meter or 30 to 45 meter per second maximum wind speed, which is slightly higher than the observed, but the tail is way off. You can normalize it and look at it again, but again it doesn't matter because they are still quite different from the observed. So obviously frustrating, but GFDL hurricane model category 4 and 5 hurricane tracks for 27 simulations. Looking at historical periods again and again and again in various ways actually helps to make sure the model baseline agrees with the historic periods, and then you can try to interpret the future. So present day 14 storms, and then you look at CMIP 3, which was used in AR4, and CMIP 5 had several differences in the models, but we won't get into that. So this is looking at late 21st century 28 storms. You can see the distribution here in terms of tropical storms and various range of Saffir-Simpson scales, 1 to 5. This is CMIP 5 with 20 storms for the early 21st century and late 21st century. Here we are only looking at the late 21st century, and you can see here these are 28 storms and 19 storms, and again quite a difference in terms of the range of number of tropical storms versus the various categories. Again, another thing to remember is that the early 21st century is dominated by model uncertainties, and scenario uncertainties begin to dominate as you go into late 21st centuries. And scenarios, of course, are based on all sorts of assumptions about population, technology, renewable energy, policies, land use, and so on and so forth, energy mixes, etc. Right? Nonetheless, late 21st century projections for tropical storms. Present day simulated occurrences here in terms of number of days per 20 years. So those are storm days. And this is the late 21st century simulated occurrence. And you can look at the difference. late 21st century minus present day. So you have a huge, significant increase over here, and there is some evidence that maybe this is true. There are changes in the North Indian Ocean, which is becoming somewhat obvious already since 2016. But again, natural variability is very tricky because in a few years, if this becomes less active in terms of total number of cyclones and cyclone days, then how to interpret the future, because global warming is going to modulate natural variability, and we can't always know how that happens. For example, trying to interpret how El Nino will respond to global warming has not had much success, because different models produce different answers in terms of number of ENSOs, frequency, duration, intensity, and so on. Okay, so base state shifts, natural variability shifts, and modulation of the natural variability is always tricky. Okay, so this is the high resolution GFDL simulation that is again showing control and warming runs in terms of rainfalls. We can say that there is a higher confidence because rainfall increase is already kind of manifest in the cyclones in terms of either slow moving, getting stuck at the coasts, or the overall increase in rainfall associated with global warming is adding to cyclone related rainfalls as well. So you can see that average radius of the cyclone and the average rainfall increase in the warming are significant. At the outer edge, the difference is not there, but as you get closer to the eye, obviously you have a significant increase in the average rainfall. This also seems to be working already in many case studies that have been looked at. So I'm going to leave it there. Sorry, but you have to read and catch up on all the debates involved there, but I wanted to run through those figures to point out some of the issues. By the way, I should make it clear that when we say relative vorticity, relative SST here, based on relative SSTs, we mean we talked about this before. There is some work by Gabe Vecchi, I think, and maybe Brian Soden that talks about how the warming of the Atlantic relative to the Pacific seems to be more important than the absolute warming. So this is based on absolute SST, and this is based on that relative SST. So you can also think of it as anomalies with respect to something as opposed to local absolute SST. But however you pose it here, relative SST is the Atlantic versus other tropics, other Pacific regions, so just be careful about that. But the question still remains, what does the cyclone really care about?